Right folks, quick video here just going through the required practical from the forces topic. This is looking at acceleration and how force affects acceleration of an object. So you've already done Newton's laws of motion, and this is looking at Newton's second law of motion, the one that says that the movement of the acceleration of an object is proportional to the force applied and inversely proportional to the mass of the object. So I'm just going to go through bit by bit what each of these pieces of equipment is for that you've seen before, but just to go over again. So I've got a glider down here. I'll move that forward there. You can see the glider. The glider's got a piece of paper on it, but the glider is the thing that we're going to be accelerating. Okay, so that is the object to be accelerated. There's also some masses stuck on there, and I'll talk to you about what those are there for in a minute. But you can see they are stuck on there with a bit of blue tack. There's also a piece of card, and I know the width of this card. That's dead important. Okay, so the glider is sat on top of this device here. This is called a linear air track, because it's straight, linear, and there's also, not that you can see on the video, but there's lots of tiny holes running along the top of it, and those tiny holes allow air to come out. Now, why would we want air coming out? Over on this side over here, which you can't see just yet, I'll just move it so you can have a look. So on this side, you can see I've got a vacuum cleaner there that's set to blow, and that's attached to the linear air track. So what's going to happen is when I turn that vacuum cleaner on, it's going to blow a load of air into the air track, and then it's going to end up a bit like an air hockey table. So if I get lots of air coming out of this, and I've got a glider on the top, I'm sure you can assume what's going to happen next. This is going to end up being almost frictionless on top. Okay, so this will then be free to move left or right when a force is applied to it. Okay, so carrying on, I've got a piece of string there. If I follow this piece of string along all the way to the other end over here, and I'm just going to rotate you a little bit, all the way to the other end over here. So I've got a mass hanger there attached to that piece of string, and I'm going to change the amount of mass on that hanger, and that's going to therefore change the force that's being applied to the object that we're going to accelerate. So I've got an object to accelerate, I've got masses that are going to act as my force to pull down at this and pull that glider along. And as you can see there, you can just about see it on the video, as this is falling down, it's pulling along the glider. Okay, so you're seeing force in action there, causing acceleration. Well, there's also a few other things knocking around as well, and don't want you to let these confuse you. There's nothing too confusing about it. Instead of us sitting down and working out what the acceleration is, because that's going to take us quite a while, we'll have to work out how fast was it going at the start, how fast was it going in the end, and then what was the difference in time between those 2 points, and we can work out acceleration the same way we have done in lessons. We're going to get the computer to do it for us. Okay, so we've got a computer set up there with data logger software on it. And we've got two what are called light gates. So there's one there, I keep turning around, and there's one there. And what this is going to measure is, as this piece of card passes through the first light gate, this device knows how wide that piece of paper is. So that means it knows distance. It's also going to measure how long it took for that piece of card to go through it, so it knows time. So this light gate here is going to send distance and time to the laptop, which means it's going to be able to calculate the speed. So it's got the speed at the first light gate. The second light gate does exactly the same thing. It knows the width of the card, and obviously that's the same as distance, so it knows the distance of the card. It also knows the time it took for the card to pass through the light gate. And it starts timing at the start of the card, and it stops timing when the card's passed through on the other side. So it's got the speed there and the speed there. This is hooked up to those two, the computer's hooked up to those two light gates, and it can work out the difference in time between those two. How long did it take to get from this light gate to that light gate, and it can calculate acceleration based on that, okay? This saves us a load of calculations, it saves us a load of recording data and slow motion video and all that. It basically just does it for us. These are super precise as well. So if you're being asked about in an exam, why would it be beneficial to use a light gate rather than just using human methods of writing down the speeds and calculating acceleration, this is way more accurate, okay? This gives a level of accuracy that we couldn't get if we were just using, even if we were using slow motion cameras, we're not going to get as accurate as this is, okay? So I think I've explained everything there, the glider, oh, no, there's one thing I haven't mentioned, all right? And this might pop up, and it's the thing that people usually struggle with, the idea that people usually struggle with. If you look at this is the equation that you've seen already, and it says that force is equal to mass multiplied by acceleration, okay? But we're not measuring force here. We're not interested in the effect on the force. We're going to change the force and see the effect on the acceleration, which sounds perfect, dead easy, doesn't it? Just change the force over there, and then it'll change the acceleration of that. That's great. Apart from, if you look at that equation, what else is in there? Acceleration is equal to force divided by the mass. So there's an issue here, because any good experiment, I should be changing one thing and then measuring the effect it has. But if I just keep adding masses to that, if you think about it, I'm not just changing the force, I'm changing the mass of everything. because the glider and the string and the mass hanger all get accelerated together. Think of them like one object. So if I apply a force to one object and measure its acceleration, that sounds good. But if I add a mass to it first and then change the force to it, well, now I'm changing two of these factors. So what I want to do is, even though I want to change the force to measure the effect on the acceleration, I want to keep the mass constant. So how am I going to keep the mass constant then? That's what these masses on the glider are about over here. So the masses on the glider that you can see stuck there, there's a couple of them stuck on. Every time I want to add a mass to the hanger to change the force, I'm going to take it off this glider. So all of the mass that's going to be applied to this object is already on it. So there's two masses on one side of the glider and two on the other, and there's one on the hanger already. I'm going to start it off, I'm going to turn it on. It's going to measure the speed there, and calculate acceleration for me when I've just got 1 Newton of force at the end. Is it 1 Newton? Sorry, 0.1 Newton of force at the end. Then I'm going to take one of those masses off. I'm going to put it on the hanger over there, and if you I'll add it all up, one mass was at this end and is now at the other. So overall, the mass has just stayed the same. But now I've got 0.2 newtons of force pulling down on that side. The masses all stay the same, but the force has changed. That makes my result more valid. Okay, so I'm changing one thing, I'm measuring one thing, and I'm keeping everything else the same. The mass is a control variable. Okay, so I do that each time. Every time I want to change the force, I just take a mass off here. I'll show you what I mean. So there's one of the masses I've just taken off the glider, and then I'd apply it to this hanger at this end. So now the force has increased pulling down on this side, but the mass of the hanger, the string, and the glider has all stayed the same. Okay, so what I'm going to do is I'm going to take that back off. I'm going to put that back over here. And I'm going to cut, and I'll show you the glider in action so you can see what's happened. Okay, I've moved you a bit closer to the setup now so you can see I've got both light gates there. A bit hard to see against the background, apologise for that. I've got the glider here and you can see where the string is attached to it as well. Okay, I've also got the laptop down there. I'll show you a screenshot of the laptop in a second just so you can see what the result was when I've applied this force and what the acceleration was. What do I want you to see here? I want you to see that with a small force I get a certain type of acceleration. Now, the beauty of this is, watching this on video, even though I'm going to give you the data for it in a second, you can just visually see what the differences in acceleration is. Every time I do it, you'll go, oh, that seemed to accelerate a bit faster than last time, or oh, it seemed to accelerate a bit slower than last time. So look at the glider as it passes through the light gates, make a mental note of, well, how fast was that accelerating? Where would I put that on a scale? Okay, so here we go. I'll start the vacuum. It is quite loud, so I won't talk during it, but have a look and take a mental note of how fast the glider accelerated with a relatively small force. Okay, here we go. Okay, so that was the acceleration with 0.1 newtons of force. I'm going to reset that and we'll have a look at it with 0.2 newtons of force. Okay, it's reset and in position now. I'm just going to show you the process of removing one mass from the glider and then adding it to the hanger at the other end. Okay, so I'm going to take one off there. So now this whole setup, the glider, the string and the hanger, it now weighs, well, 10 grams less than it did a second ago. But if I come over here and apply this to the hanger, which has fallen on the floor, so I'll apply that to the hanger, and put that there. Well, now the mass of all this is constant. It's exactly what it was before I started the experiment. Okay, but now what happens when I turn the blower on, it's going to be pulled with a force of 0.2 newtons. So I've increased the force being applied, but I've kept the mass constant. Dead important you understand that. Okay, I'll bring you a bit closer and you can see the second run. Okay, so here we go with 0.2 newtons of force. Again, just keep your eye on the speed, the acceleration through the light gates. Did you notice the difference between 0.1 and what I'm now about to apply, which is 0.2 newtons? Keep your eye on it. Okay, that was 0.2 newtons. Let's reset, go for 0.3. Okay, 0.3 newtons being applied now. See if you notice a difference with the acceleration. I think there might have been a bit of friction there. So you might have noticed that the second one seemed to move a lot faster than the first. The third one seemed to be a bit slower. Now, there's a reason for that, and that's because there's a bit of unwanted friction where the string is rubbing through the eye at the end of the linear air track, which is a bit unavoidable, to be honest with you, in the setup that we've got, in the equipment that we've got. But that's something, it's pointing out what could happen, why we want this to be blowing air out, why we want a frictionless environment, because now we've got an inaccurate data point, because, well, applying more force, we've seen so far, and we actually know already, applying more force leads to a bigger acceleration, and That's not what we've just seen there. We'll reset that again, see if we can get it to do a proper run so you can see what it would look like with 0.3 newtons. Okay, 0.3 newtons now. Hopefully you've seen a pattern emerge. This one's going to be 0.4 newtons. Keep your eye on the acceleration again. Okay, so here we go, 0.5 newtons of force. Keep your eye on the acceleration. Okay, what I'm going to do is, I will give you the data that I'm going to collect off the laptop. I can't really show you the screen, it's going to be a bit blurry. So I'll give you the data and I will hopefully be putting that up on screen now. Now, if you look at the required practical sheet, it gives you step-by-step instructions of how you should process your data. It wants you to put it in a graph form, and then in a 6-mark question capacity, they might ask you what might you do differently, what results might you expect, what are the sources of error during the investigation. And there's a few sources of error in the investigation. So one could be, what happens if I've measured that piece of card, this one here, what happens if I've measured that piece of card incorrectly? I've told this that that's 10 centimetres in width. What happens if it's 11? So immediately the speed that it's calculating is now incorrect. That might be one of the reasons that this is incorrect. The big one with this, the biggest issue that we have with this, is unwanted sources of friction. Okay, so you might have noticed there, and I've kept it in on purpose, that the last one, 0.5 newtons of force, didn't seem to accelerate at the same rate as the other earlier ones did, especially 0.4, that seemed to be perfect. And that's because where the string is passing over the pulley at the end of the setup, there's a bit of unwanted friction. I ran it a few times and I still couldn't get it to get rid of that friction, but it's fine because you've now seen what can happen. With unwanted friction, I've just got an inaccurate piece of data. What would you do if you were doing this in the real world, in science, in a lab? You'd repeat the experiment, wouldn't you? If you've seen that there's an obvious source of error, you'd repeat it and try and remove that source of error. Okay, so what I'll do is I'll pop the data up. You can have a look at that data, but what is the conclusion that you should reach from this? Okay, so in a nutshell, the force applied to the object, in this case it's the glider, is proportional to the acceleration of the object. The bigger the force I applied, the bigger the acceleration of that glider. That's what you should get from this. Okay, so I'm going to wrap that up there. You can have a quick look at your data, you can plot your graph if you want, but that just about covers everything.